models. Okay, yeah, excuse me, I see that I've forgotten to record. So the recording has started. The idea is that in both logistic and linear regression, you have a plane that will define the regions of both classes. So it's still a linear separation, but the criterion and the model behind obtaining this line is different. Okay? So today we will continue by first introducing how we can do multi-class classification. So instead of having reds and blues, we will introduce the ability to have a third class or even a fourth class. And I will also explain how to do proper model selection. So how we will validate models to select the best ones. And I will also speak. So this is one topic for today. Another topic will be overfitting. So basically the curse of dimensionality. Okay. So what I will do, I will maybe first present you, before we go to the theory, I will show you a practical example of what we have seen yesterday and the lesson before. So let me just share a notebook. I will maybe zoom a little bit for you. Do you all see the screen? Yes? Okay, thank you. So I want to show you how we can basically retrieve the concepts we have seen with Python. So let me first stop my video here. Okay. So imagine you have two different classes, the blue and the red ones. And I have used Python to create these two classes. So basically, I have defined two descriptors, so two features, x1 and x2, which is a random number of points. So this function will return a random point between 0 and 1. So I multiply times 2 plus 1. So these are the blue points. And the red points are defined in the same way, but I do a shift plus 3 that is a bit bigger than the other one. For the second dimension, I do almost the same. So here's times 3 plus 2 times 2 plus 3. So the idea is that these second points are farther away. And so these define the red points. So this is an idea to create these two classes. And now we can see how our models react to this kind of data. So the scikit-learn library, which we will use for the most of the upcoming lessons, is very useful to quickly experiment with the models we see. So we can very easily import the linear model, so the linear regression model here, or you can also import the logistic regression. And one model we will see, I think it's on Tuesday, is the support vector classificator, which is a third model that you can easily import with scikit-learn. And so what you see is that you can simply define the model as the corresponding class. So you make the object, and each of these objects has a fit function and a predict function that is here. And so you can easily change models. So what I want to show is that here in this example, I've made data that is linear separable. So there are two well-defined clusters. So I think you are agreeing with me that you can define a single line that divides the two classes. So let's see how the linear regression reacts to this. And so normally if I run, so let me define the data first, I plot it. Okay, so because it's random, each time I have a little different data. So still here you see it seems still to be linear separable. You have a line here that should be working. So I fit my model on this training data. And what I also do is that I make with NumPy measure it, I predict on all the points what my regressor is giving. And so when I do this, what you obtain, so it takes a bit of time, here you go, you have the solution from the linear regression with 3 lines. So remember, we have one line that is fitted on the 0, one line on the 1s. So remember in the lesson I said -1 and 1, and I said to a question that is not something you are mandatory to do. You can take 0s and 1s. This works too. And in this case, the line that defines the boundary is a line 0.5. So this is a boundary between the two classes. You see that still we have a mistake here because the blue is on the other side. Because it's quite close, and due to the fact that we have this mean square error, we are a bit pulled to the reds. So I can do a second run. So it's still quite close. Let's do. Okay, here it seems a little bit better. Let's try again how the model reacts to this. Okay, you see here we have a clear separation with the linear models with the least square classification. So this seems to be working well on this data. Now, the next thing we can try is to add 3 points that are a bit separated from the other ones. So let me generate this data again. Okay, we have this data. And let's see how the linear model reacts to this. So you see here it's still well defined. So we have a boundary that this seems to be at 0.5, so it's still good. I was a bit lucky, so maybe let's try again. So here you see, okay, definitely here we have an issue with the classification because, like I explained in the course, it's a typical example where the mean square loss is pulling this boundary towards these points. So it's not the best criterion. So what I can do, for instance, is change the model here in Python to the logistic regression. So remember that now we don't have a continuous space that is mapped from -infinity to +infinity. No, logistic regression is mapping to 0 and 1. So it's bounded between 0 and 1. And so you see that the solution is much better in this case. We have a clear distinction between a whole space that is 0, a whole space that is 1, and that is much less affected by these outliers. Okay. Now, you could also have examples where data is not linear separable. So here there is, okay, here it's almost not non-linear separable, but imagine that it's even worse, that points are overlapping. And how did I do that? I just added more noise by multiplying the randomness by a greater factor. And when I do this, you see that the boundary is not perfect, of course. And we could also, okay, sorry. So here I had not used a linear model. Let me use the linear regression. Okay, here is the solution. So you see again, it's minimizing the sum of squares. So it ends up to be somehow in the middle of the clusters. We can have a play with the logistic regression. And we have something like this. You see, the next step will be to introduce the support vector classification. So this is work that we will do on Tuesday. So this is another model. And we will see, we will define what is a kernel, and we will define also this vector mathematically. But the idea is that if it's linear, you still have a linear model that separates boundaries, but we will see that we can go to non-linear kernels. For example, like this, and we will be able to make boundaries that are non-linear in nature. So this is two-dimensional, but you will quickly see that this works for any kind of dimension. So two-dimensional is always a good idea to start with the models to see how it reacts. So this is something you can easily visualize. I can make contour plots to see how the boundary decision is changing, and also how it reacts to data. So, but the idea is that you can, of course, use these models to higher dimension. Let's see if we can make something that could be separable. Okay, I could maybe use one of these. Okay, I think here we could make a curved line that would work. So let's try to see if the support SVC with an RBF kernel. Okay, you see here it's almost closely classifying these samples. So what I suggest you to do, so I will share this notebook at the end of the session with you, is to play with the different models, the different data distributions, and see how everything is working. Are there any questions about this? It's the moment to ask if you have questions. Okay.
Sorry, I have a question.
Yes.
So this is new to me, the machine learning thing. So I see you keep running the code several times. Is there like a specific criterion for you to know that this is the best fit that you can have for the code? So
here the only reason I'm running multiple times is because I have a random function in my code to generate the data. And I'm just looking at how the points turn out to see a bit what I want to do. In machine learning, most of the time, the points you collect are fixed and don't change from one time to the other time. Here, it's just because I'm randomly generating points. Okay.
Okay, thank you.
You see, so each time
I had well-defined data that then you wouldn't have to run several times.
No.
Okay.
It would be a single time. Of course, models themselves have also random seeds in them. That's something important that we will see. In fact, each time you define a model, we have seen you have these weights, and these weights are initially put to some random number, and depending on this random number and the stochastic gradient descent you will perform, you can end up to a different solution. So keep in mind that you also have this randomness inside the models, but often this is something you can manage by validating the models or having an ensemble of models, but this is something less drastic than what's happening here in the data. Any other questions? And so basically regression works in the same principle. So here I demonstrated for classification, but for a linear model, when you see the output of the model, so let's run this again. I have decided to put only 3 contours, but technically you can remove this. And you see that, in fact, it's mapped into a continuous space that goes from minus infinity to plus infinity. So it's continuously giving values. When you do regression, of course, what's happening is that you regress through these values. Okay. In fact, I will start with this part first. Not this. Okay, here. So before overfitting, let's present you the multi-classification problem first. Multi-class classification. So suppose we have, again, a two-dimensional space, and we have three, or let's even make 4 different classes in that space. So I make this hypothesis that they are well separable. I have some crosses here. How would we be able to classify between the 4 different classes? Has someone an idea of how we could do this? What we have seen before, of course. Remember, we have just seen the ability to make a single boundary between. Yes? I think someone was speaking. Yeah, I don't hear you.
Hello.
Yeah, hello.
Hello.
Yeah, hello.
Yeah, we can use a circle around the clusters.
We can use what?
Circles around the clusters, the 4 clusters we have there.
Yes, and what did you say before the 4 clusters? We can use
circles. You make a circle around them.
Okay, yes, example. Okay, this is, you will make a circle around each.
Yes, yes.
But how do you do this mathematically with what we have seen before? Because we haven't seen the ability to make circles, but we know how to make simple lines between different classes. So in fact, the idea is that we will define a one versus all approach. So what is this? There's one possibility. There are different possibilities, but
Hello.
all is that in fact you can.
I think we can do partitional clustering of each part.
Okay, that's a good. It's a good answer, but here we are in the supervised machine learning lecture. So the idea is not to do clustering. Clustering is something that is unsupervised, where you try to see trends on unlabeled data. Here, keep in mind that the data is labeled. We know that these are triangles, crosses, squares, and circles. So we know what they are. So we don't need to cluster them. They are already clustered by the labels. So the one versus all approach is the idea that you transform a multi-class classification task in a binary classification task. So if you want to detect these, what you do is you translate these as the first class. And the second class will be the other ones. So these, the crosses, and the squares. But they all have the same label. So we have here 1, and there we have the 0 class. So we have transformed the problem in a binary classification. And so we can here define a boundary, or later on we will see the nonlinear boundaries, but you can easily classify between both of them. And you do this for each of the classes. You have a second one where you can put the blue triangles, and then the other ones that are the crosses, the squares, and the circles. And here you again put a boundary. That here it's nonlinear, it should be like this, that defines both of them. And so we have defined, or we have simplified the multi-class in 4 sub-problems. So we have this, now we can have the squares, the other ones, and then we also have the crosses next to the other ones. Okay, do you understand this? So the idea is you just have 4 models, you run all the models, and then you look at the one that gives you the highest probability to have that class, and then you can easily predict which one is, or what is the class you want to predict. So mathematically, you have model 1 that gives you the probability of class 1. We have a model 2 that gives the probability of class 2 versus the rest, then for 3, and then also for class 4. So we divide like this. So I think this is the most important strategy, just so you know there are other ideas that make all possible pairs. You can make a pair here, a pair here, a pair here, a pair here. So there are a lot of pairs possible. And for each of them, you make a model 2, and then depending on the output, you can again process. But the key idea is that you can always make binary classifications to make a multi-class classification. Okay, now we can continue to the next topic of today. It's the topic of overfitting and curse of dimensionality. So overfitting is the idea that learning the data so well that the model is not useful anymore. So it's working too good on the data we give it. And so we have issues on new data. So it can occur in classification and regression. And it's one of the main important concerns in learning. So that is really an important point of attention you need to understand in machine learning. Let's see an example. So we have, again, the example of the salmon versus sea bass with two features, lightness and width. And I have three models. I have a linear model, I have a nonlinear kind of polynomial model, and then I have a high complex model that is able to make a perfect decision between all my points. Which one is the best, do you think? You can put in the chat 1, 2, or 3. Okay, I think most people are agreeing that 1 and 3 is somehow the best. I see, okay, it's funny. I see all the numbers. So it's, of course, something that I guess people define personal what they think is the best. So I didn't really define as best, but from a machine learning perspective, this is clearly not something that is good, because you are making it so good that probably you're not generalizing good enough. So I will now explain why or what that precisely is. So this is not a bad model. It's quite a good model, but it's quite simple. This is a good compromise, like I said, and this is too perfect and is very dangerous because it could predict very wrong points in the future. So another example is a model where you want to fit the blue points. So the blue points have been made with a sinus and a bit of noise, and you can have a polynomial of degree 0, so it's a constant value. You can have degree 1, which is a straight line, degree 3, and 9. So again, you see, here it's interesting because you can see what the true value should be. So this model is quite good. This model, which is very good at predicting the blue points, is in fact very bad at predicting the points between the blue points. So here you see you're far off, and same here. It's too good, and so it's going crazy at the regions that are between or next to the blue points. So at extrapolating, you are very bad. So why is this not a good idea? So I just explained, because nobody cares about having a model that reproduces the output. You know it already, so there is no point of having good predictions at the points you have. The goal is to get a model that performs well on the new samples. So we want it to be good between the blue points. So here it's not good between the blue points. And so this is a model that is overfitting the data. It's too good, it overfits the points. And so we have bad predictions on new samples. So don't forget that the only samples that are known by the machine are the blue points. And the green is not known by the machine, of course. Okay, so does everyone understands this? So now
Pardon, I have a question.
Yeah, go ahead.
When optimizing the overfitting, should I have to measure only the mean or standard distribution?
Okay, so this is the next part. So the next question, so you will have the answer later on,
Okay,
is how can we define this mathematically? So here, okay, we have the idea that we want to be good also at new points. And so how can we do that in practice? But the idea is to define a certain error function. So first of all, we define an error function that is defined as the sum of the squares. And what you do is that we compute this error on a training set and a test set. And this is really important to know, is that the training points are the blue points, so the points that are given to the machine, and the test points are new points that we can pick. For example, here we could have picked any point on the green line to see how good it's doing. And so by comparing the test and train sets, we can define how good the model is doing on new data and if it's overfitting. So you see here on this plot, this error criterion in function of the model complexity. So imagine we have this example. You see that if you increase the complexity, so increasing the complexity means that we go from this to this to this, so we have a better fitting. Both training and testing are decreasing. But at 9, so 9 was this model, what you see is that the test is going very up and the train is going very down. So this is a very clear key point of overfitting. So when you see a big difference in testing and training, so testing is very bad, training is very good, you are overfitting the data. So I have a question. I don't understand why number 2 is not good. So I guess you're speaking about this here. So why is it not good? Because probably the real trend is something like this. This is maybe something that is not realistic enough. And in the future, what will happen is that you will have probably a lot of black points here that will be wrongly classified. So probably these points are just exceptions and you should not put your boundary decision like fixed to that direction. So you're really taking these points are very true points, so maybe you don't need to take them. So this is why it's not a good model.
Okay, thank you.
So one thing you can see is like this. This is a clear trend of overfitting. Let me mute the, maybe one person is making noise, okay. Another point you can see is the weight. So when you look at the weights of the different models, so again, we have the same example as here. You see that when the model is getting more complex And when you observe overfitting, the weights are getting very, very large in magnitude. So you see here, it's thousands of even millions in magnitude compared to here, weights that are close to 1 or 10 here. And so large weights are something that shows you that there might be overfitting going on. Why? Because large weights try to compensate each other such that at the exact point where you have a training point, everything compensates to have the right prediction. And then, but if you go a bit beyond that point, you have a crazy wrong result. Overfitting is something that is very dependent on the number of samples. So let's take a polynomial of order 9. If I take 10 points, I am overfitting. If I take 15 points, I'm still overfitting, but you see it's not that bad. And at 100 points, a model of order 9 is very good, in fact. It's not overfitting at all, and it's giving you a good solution. So the risk of overfitting is something that is, let's say, dependent on the complexity of the model. So let's put this here. So it's the complexity. It's dependent on the complexity of the model and the size of the learning sets. So if the model is more complex, you have more chance to overfit. And if the training set is larger, you have less chance to overfit. Okay? So how do we avoid overfitting? One thing is, and this is something that is often done, is that you repeat this thing, this training testing idea for different models, different complexities, and you always measure training, testing, and you try to avoid big differences. You try to have something that is quite similar in magnitude. So trial and error of the different complexities. This is, by the way, something that is done. So I will later on explain what is cross-validation. So this is part of the cross-validation. You validate the models and see which one are not too complex or not too simple. This requires, of course, a validation set. So validation set is not the same as test set, as we will see in just a few minutes. Test set is to test the final performance of the model. Validation is what you can use to tune and change the complexity and all the parameters. So a second solution is to use regularization. So what you can always do is, because I just said to you that overfitting is when the weights are getting very large, what you can do is, in the loss function, we have seen that we have the sum of square criteria, and we will now add a second term that gives you lambda divided by 2 times the magnitude, some magnitude function of the weight. So it can be here, it's squared, it could be an L1, an L2, or any kind of norm of this vector. The idea is that when the weights are big, this is big, and so you have a big loss. So remember that by gradient descent, we want to minimize this as low as possible. So we want to minimize this as low as possible. And so we will have weights that are low and so less prone to overfit. So lambda penalizes the error by some complexity measure. So other complexity measures are possible. Like I said, L1 norm, L2 norm, or any function that penalizes the magnitude. And of course, you need to fix lambda. So what is lambda? Lambda is something that will define the importance of this. So if lambda equals 0, this has no effect and you don't regularize it at all. If you put a value that is higher, so you can go to 1, you can go to 2, you can go even to higher values, what is happening is that you put more weight to this and regularization will be very important. So lambda is something I cannot give you good value like this. You should validate like any other parameter to see how important is the regularization in your loss function. So it's something that has to be defined through validation. Okay, so now you have understand what is overfitting, how you can avoid it. So keep in mind to very well monitor this quantity to eventually add regularization. And now I can show you why overfitting is such easy to do in high dimensional space. So we have seen that overfitting is something that depends on the complexity of the model, on the size of the training set, but it also depends on the dimensionality. Why? Because suppose we have a two-dimensional problem, so 1 and 2 dimensions, and we make a very simple algorithm that is making boxes on a regular grid, and you color the box depending on the points you see. So here you see a lot of blue. This is the blue region, blue, blue, blue. Here you see majority red, so you put red boxes, here green, etc. So you have some kind of map that gives you the class depending on the majority of points. So this is working quite well in a two-dimensional case. But if you go in 3 dimensions, you see that you don't have a grid. You begin to have 3-dimensional boxes. And if you go in even higher dimensions, you see that these boxes are hypercubed in higher dimensions, and you tend to have less and less data inside. So due to the high dimensional growth, so it's really an exponential growth of space, and you have to imagine that you have so many dimensions that points are becoming alone in this high dimension space. So you don't see a lot of points. There is a lot of void in high dimensions. And so it's really easy to have something that is close to this instead of that in high dimension. Because in high dimension, you only see void, 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 void. And so you tend to overfit. This quite of dense amount of data is something you can only see in very low dimensions, in 2D, 3D. And when you go beyond, you only see void, basically. So that's why overfitting in high dimension is something that is quite common. And so this idea that the space is really growing fast and that you have a lot of void is the idea of curse of dimensionality, that dimensionality is really making the problem quite complex. So in practice, we never have enough data in high dimension. And it's it's really important to look at overfitting. So never forget that machine learning is used for high dimensional data. So we are really in this kind of problems. And that basically for very low dimensions, like 2D, 3D, machine learning is not that used in the sense that you can have polynomial splines and things that are probably more suited. Okay, so this ends the part about curse of dimensionality. Any questions?
Hello.
Yes.
Yeah, my name is Christian. I'm from the University of Rwanda. So when you say about dimensionality, the 3 dimensions and more, do you mean you are taking 3 parameters or 4 parameters into account?
Exactly. So when I think about high dimensions, the thing is dimensions it's very easy. It's the number of features you have. So if you have 5 features, you have a 5-dimensional model. So if you have, let's say, a machine learning model, you predict some y. Well, the number of features, so you can go up to 5, and often you go to hundreds, if not thousands of features. This is the dimensionality of your problem.
Okay, thank you.
So reducing the dimensionality is something that is really important if you can do that. And so that's why, that's maybe something I should have said, feature selection is important. So feature selection is the idea that you select, and you can also have other techniques like dimensionality reduction, which is mapping features to new features. But if you say, okay, this is not important, this is not important, oh, this one is in fact the same as this one, so I can remove one of the two. Okay, and then if you do like this, you end up with a smaller list that is much smaller in dimensionality. And that is a good thing to do because you are less prone to have effects of the curse of dimensionality.
I just have another question from what you just mentioned. Aren't these features supposed to be linearly independent from each other? Just to consider them features.
Yes, that's would be ideal. In practice, it's difficult to have features that are perfectly independent. And when you, I don't know how the data is made, but if someone gives you data or you generate the data, the features, you will have to look at how the features are related to each other to eliminate maybe some of them or to reduce the dimensionality. So you can perfectly fit, you can make a model with linearly correlated features, but it's not the best idea, of course. So
okay.
that's why selection and reduction is an important thing to do too.
Hello, sir.
Yes.
Hello. Please, can you give an example of the features, just to understand more of the dimensions?
Okay, an example.
Yes.
So imagine that you're taking a molecule as input and you want to predict some, I don't know, some formation energy or some property that I will call E. We can, for instance, put each atom inside, and we could say, okay, I give the atomic number. So let's say we have an oxygen and we have something else. We have some number I just take some random numbers here. And then you also put the mass of each of the points. So I don't know, I put something that is the mass of the atoms, but what you see at this point is that the atomic number is very related to the mass of each atom. And so you quickly have something that is high dimensional, and you could easily not put these ones or these ones, so these may be redundant, and you can remove one of the two. So the features are these numbers. So there's 1 feature, 2, 3, 4, 5 features. And the idea that you can remove some of them is that they are correlated between them. And so you can remove, for instance, the atomic mass and only keep the atomic number. Okay?
Thank you.
Okay. So here is a quick reminder about the task, but I have already presented this. So you have either classification or regression. So classification is discrete classes. Regression is we have a continuous target to predict. They're not so different as someone said to me, because the idea is that you, in fact, in machine learning, everything is a kind of regression because you can only work with continuous variables, but still we are able to make classification models. Clustering is another technique in machine learning. This is not part of this of my part in this in the lessons, because this will be seen later. It's unsupervised machine learning. And you can also do filtering, that is again selecting points to have only keep, let's say, the relevant information, but this is something we will not do in this in the lessons. And another unsupervised technique that is also part of machine learning is to do dimensionality reduction. So projection is one of the techniques to do dimensionality reduction. Is the idea that you go from a 3-dimensional space to a 2-dimensional space. And here it's very easy to do because you see that you have in fact a kind of manifold that is inside the 3-dimensional space. And so you can easily in 2D go along this data and reduce the dimensions. This is something I will not go more into detail because it's not part of my work here. And so this is already explained, supervised, unsupervised. Okay. So now I will go to the next part, which is model selection. So it's very related to what we have seen with so it's in fact a bit continuous. It's a continuing topic of the overfitting. The question is, how do I select the model between several ones? So when I say that, it's very large in scope because you can choose between, for instance, linear regression, SVM. So that's something we will see later. We can have a random forest. I hope I will have time to introduce this too. We can choose between an artificial neural network, any model. But inside the model, you can also have linear regression with 5 features. Why not 15 features? Maybe you have the features, so why not go further? The SVM, you will see, you can choose which kernel. Do I want to have a linear kernel, a nonlinear, which nonlinear, a Gaussian, a periodic kernel? Do I want to use which type of C? For the random forest, how many trees? The depth, you have so many parameters. Artificial neural networks, there are a lot of parameters like the number of layers, number of neurons, activation functions, the batch, etc. All things you can choose, and each of these parameters are called hyperparameters, are things that you have to choose from the beginning. Even before learning, you have to choose how many layers, how many weights, etc. you want to take. So model selection is something that is very important and is very large in nature. It's really the idea to optimize a set of parameters you have to define from the start. So this is the question we want to answer today. So let's suppose I have a number of points in 2 dimensions. No, sorry, here it's in 1 dimension. So we have feature is X and the target is Y. We could use a linear model. We could use a quadratic model. So you see, it seems to be a bit better. We could have a quadratic model without independent terms. So with that, I mean that we start at 0. So the plus B is 0. And this is the one I use to generate the data. You could use a 5th order polynomial. So this would be something like this. So how do I know which one is the best one? So you see it's very related to the problem of overfitting. So the only point that we want to do here is to not overfit the data. And so I will define here a few notations. So we say that we have an input space X that is of dimensionality D. We have the target Y, and we have a function G, which is the machine learning model that takes X as input, returns Y, and some parameters theta. So theta are the weights that you can obtain by learning. So it's the gradient descent. But the hyperparameters, like I said, is all these things I've noted here. It's, for instance, the number of features I take. So here you see you have a third feature, which is X squared. And you have a lot of different parameters like the number of trees and the random forest, etc. So how do you know how to choose that? So this is called here alpha. Alpha is the hyperparameter. So what we do is we define an error criterion that we will use on unseen data. So like I showed you, we use this on data that has not been seen by the model. And here what they define is the generalization error that is defined as the square of the difference. So the sum, here is the mean squared error, basically, which is a well-defined criterion. And so ideally, you want to use all new possible data, but of course, like I said, we don't have all the data at hand, and so we use a test set with some few points where we compute this MSE on. Okay. So you also have in practice the MIE, which is also often used. The MIE is the sum of my prediction minus Y, and you take the absolute value of this divided by n over all my points. So you see the difference is that I don't have a square here, and I take the absolute value. So how do I need what I have to choose? It's basically often a question of what do you want to optimize, and you have to know how they react. This is more sensitive to outliers. So outliers will have something that is squared, and so you will tend to penalize outliers more strongly than MIE, where you will have something that is more equal to each point. I would suggest you to look on the web on other, let's say, loss functions, or even loss metrics, I would say. So metrics on how to assess the quality of the fit. So I will first skip this part. So this is, okay, I can go quickly through, but I will keep the slides for you so you can read through them. But the idea is that one thing some people do is next to this squared criteria, so next to the MSE, you have a penalizing term that is penalizing the dimensionality of theta, so the number of weights. And so intrinsically, by minimizing this term, you also minimize the dimensionality, and you tend to choose simpler models. So for instance, in our example, when we compare the linear model with the quadratic without independence, you see that these two, so ICBC are these two functions here. So it's just the MSE plus the dimensionality. It penalizes quite strongly this fifth order model, because here you have 5, and therefore it tends to not use this one. Okay, no, so it's still used. That's funny. So this model would be chosen in both cases, and so you see it's maybe not the best criteria in this case, in this example. So this is in practice less used, so that's why I'm a bit skipping this part. Instead, this one is quite important. So it's the idea of what I explained to you just before. So validation. So what I do is I have my whole data, and I make a split here with all the data on the left is used for training, and the second one is for testing. And this error criterion is this one I've showed before. It's the mean squared error. And by doing training on one part of the data and testing, or here, sorry, it's validation on the second part, we use the model that has the lowest MSE on the validation set. And if you do this on that part, what you see is that we still have, so we have quite low score, but we still will choose the 5 order model. So maybe this is the best one following this criteria, but we know that we made the model with this. So ideally, this would have been chosen, but it's not the case here. So what we will do to have something that is less, let's say, sensitive to the points we choose in the validation is that we do cross-validation. So you see now, here I just have put validation, and now we go to cross-validation. And so instead of having one single validation set, we take a number k of random repetitions of the validation. So we can put it here as the first time. The second validation can be there, then can be there. So it's totally random repetition of the validation data. And the idea is not complicated. You take the average over all validation sets. So this, remember that this is the squared error criterion on a single, so it's on a single validation set. And then we use another average that does it over all the different sets. Now, when you do this, and you have a high number of random repetitions, you see that with here, the lowest score is given by the quadratic model. So you see that this technique is quite good. We are finding that this model is the best, but you see we still have to repeat a lot of time this random set of validation points. Something that is much more done in practice is the Kfold validation. So the Kfold validation is very similar to the cross-validation, but with the idea that you systematically split the data in different non-overlapping validation sets. So suppose we have endpoints. What we do here is that we cut the data set in k different splits. Okay, so you see each time is a split. And what we do is that we will use the first split as validation and all the other ones as learning. This is for the first fold. We call this the first fold. And then for the second fold, what you do is that the validation becomes the second fold. So this is the validation. And you train on the other one. And by doing this k times, each fold will be used as a validation set. And all data will be used as validation. So you have something that is much more average across the validation points. So make sure that each data is used once and only once for validation. And so like I showed you, the second step is this. So the first step was to use this as validation. Second step is use that as validation. So you make, in fact, a loop over the different folds. And for each of these folds, of course, you compute the generalization error, which is this function here. It's the MLESMD function. And here we do this for each of the k folds. So here I divide by n over k. Why? Because I have n divided by k samples in my test, sorry, in my validation set. Okay, I think this thing is something that you will certainly do in practice, Kfold validation. So I want to be sure that everyone understands this idea. So I will just maybe show the results. I don't have it on my example. Okay, so maybe one last comment is that you can have So the common thing to do is to have 5-fold or 10-fold validation. So this basically means that you make 5 different splits. 10-fold, you make 10. But imagine that you make as many folds as you have samples. That means that you make splits around each sample, and you have one sample, so 1 point in each of the folds, 1 data point. This means that you train on everything except one, and that you test your model on 1 point. And then you repeat again, you remove another point, you train on all the points except one, and you validate on 1 point. So you will each time train on all except 1 point and validate on that one point. And you repeat for all the points. This is called leave one out cross-validation. So this is something that is done also for validation. But here it's not always the best idea, because you see that doing that can lead to overfitting too. So here, for instance, the fifth order model would be chosen as 0.2. So the most used cross-validation scheme is either 5-fold, 10-fold cross-validation, and this is something you should really well understand. Are there questions about the Kfold cross-validation?
Pardon, I have a question.
Yes.
Thanks for discussing model selection and cross-validations. I have a question. Error is the leading factor for performance metrics. When it comes to measuring error, I have these questions. The error range, is it from -1 to 1 or -2 to 1?
The error range?
Yes, the error range, scientific error range, because this.
So
for me, this is the first question.
So you mean this, the scale of this?
No, in general, as a concept, the error.
So in general,
can I say the range for the error from -1 to 1?
It's something I cannot say in advance, because the range can be anything for MSD and MIE, because you just take a difference of a continuous variable to the square divided by the number of samples. So it's an average that in principle can be any value. But if the good thing is that it's often has the same scale as your target. So imagine that you predict the band gap. Well, the band gap can be from 0, let's say, to, I will just take a quite arbitrary value. It can be even higher, but let's say 10 electron volts. So the MIE will typically not be much higher than that, and will be on the order of, I don't know, something 0.3, let's say. And here the advantage is that you conserve the same units. So it has the same units as your target, because here you take the absolute value. Here is the units squared. And when you take the root mean squared error, you have still the same units. So that is why RMSE is more used. But it's not 0, 1. It's something that depends on the scale of the target.
Thank you so much, because this is confusing us a lot. When we're running, we see the range of our errors.
Okay, so
something beyond -2.
Okay.
And above 1.
It depends on the metric you use. If you use MSE, if you use MIE, it can be anything. If you scale the outputs, then it will be, I guess, around 0 and 1. But the only way to have something that is between 0 and 1 is to compute other metrics like accuracy or I don't know, or some kind of correlation between target and true value. So maybe what I could do is I will maybe try next course to list all the metrics you have and how they are bounded and how they react to different things, because this is, I think, quite important to understand in practice.
Okay, thank you so much. Also, sometimes we are confusing to reorder RMS, which is the more valuable, RMSE or MSE or MAE or generalized regression error.
Basically, RMSE and MSE
Yes.
are the same in the sense that the one is the square root of the other one. So these two, I can see them as the same. But the MIE, like I said, the biggest difference between these two is that the one is squared, so you are more sensitive to outliers. So if you don't want to make bad prediction on some of the samples, you should use MSE. So if you are sensitive to, let's say, big deviations, but in general, what I use the most is MIE, because you give the same weight basically to all points. Okay.
Thank you so much. Thank you so much.
I will try to make a summary on that. Okay, so because I have some limited time, I'll have to end in 5 minutes. I just want to see one more thing with you, is the metrics for classifiers. And then I will have to leave you, but let's first discuss quickly this idea of classifiers. So when you do classification, it's better to have something else as a metric. So what you can do is compute what is called the confusion matrix. So what you do is that when you have a model, you can have a true sample that is identified as true. When this happens, it's perfect, and we will put it in the matrix here. So all the points, we will sum all the points that are true and classify true as this element C11 in my confusion matrix. If my point turns out to be classified as false by my model, I use another element that is element C21 in confusion matrix. So it's the number of points that are true but classified as false. So this is in fact a false negative, because basically it was true, and so we will put it inside element C21. We can do the exact the same for the negative. So a negative that is classified as a negative, so let's say it's class 2, classified as class 2, is element C22, and an element that was false but classified as true is put here. So the confusion matrix is a matrix. You can also draw it as four. It's always 4 elements. So 1, 2, 3, 4. And you have basically all the
Pardon, there is a noise here. Kindly off the mic. There is a noise here, please.
Okay, I will mute who is making noise. Okay, good. Yes, sorry. Okay, so the idea is that here you count the true positives, the true negatives, and then you can have, of course, false positives and false negatives. So the idea is that you want to have very high values at the diagonal and very low values here. So you want to be good when it's true, it should be true. When it's false, it should be false. And the other possibility should be low. Sorry, this should be low. Okay, so I will maybe go back to that on Tuesday, because I was quite fast on the confusion matrix. And so, like I said, the true positives is C11, the false positives is C12, true negatives is C22, the false negatives are C21. So you can really classify depending on how they turn out. Precision is something that is defined as the number of true positives on all the positives. So it's on all the the positives that has been classified. So basically, when you have a classifier and the classifier is saying it's true, the precision gives you how many points of true are really true by this classification. Recall is something that measures the number of true classified on the total number of true points. So this means that on all the true that has been given to the machine, how many percent is indeed found back to be true? So how many has been recalled back to the machine as being true? Okay, and so the accuracy, this is also often used, it's the diagonal. So it's the sum of the diagonal divided by all the points. So all the points, it's just, if you take the sum, it's the number of points n you have in your data set. And so an accuracy of 0 is bad, and an accuracy of 1 is good. So it's the best you can have. Okay. I think I will end this class here. I just wanted to be sure to see this quickly because you will use it through the homework to classify or to let's say to evaluate in homework 2 the logistic regression. But you will see this is all implemented in scikit-learn. So you just have to call a function and it will return you this matrix, but be sure to understand what these values mean. Yeah, that's basically it. So for maybe to be sure that everyone is understanding the homeworks correctly. So the ID, but you will receive an email with the details. So I will send you after the course also the second homework. And you will have to submit by email your solution to me. So the deadline will be, I think we will fix it on Monday 2 p.m. So you have the weekend to do this. Monday 2 p.m. you will have to send it to me by email at last. And you only send me one, if you want to be corrected, you send me one notebook per homework. So this means that you send me 2 files and I will correct them. And an important thing, but everything will be sent by email, is that you put your name inside the file name. So it will be last name underscore first name underscore unsupervised underscore homework 1, for instance, dot IPython notebook. And you do the same for the second homework where you have a 2. And this you send by email, and so I can correct this. But don't worry, I will send by email the exact procedure and deadline again, so you can send me that. Okay. Yeah, I will specify everything in the email. So you will have everything in the email. So
excuse me.
Yes.
My weekend is actually Thursday and Friday, and I work on Saturday till Monday.
You will not have the notebooks are very small normally. So I mean, you can do it in 1-2 hours, I think, or in one morning.
Homework 1 or 2.
So you're not able to make it for Monday 2 p.m.
I will try, but you know, I have what is called the supervisors for exams. We have the control for the next week from Saturday till Thursday. I will try to do it, but I want to tell you that I don't have a weekend. I already finished my weekend. Thursday and Friday is my weekend, and I start working again on Saturday. I will try to submit them in Monday. I hope.
I will. I know. In fact, I'm not available Monday too. So let's make the deadline. Okay, I will not change this before next lecture. So I think the next lecture is Tuesday, 2 p.m., right?
Yes.
So everyone has to submit it before the start of next lecture. So Tuesday, 2 p.m. is the last day you can submit homework 1 and 2. Okay? I will extend by 1 day. So you have up to
Hello, sir.
Tuesday, 2 p.m.
Hello, sir.
Okay, good.
Hello. Hello.
Any other questions? Okay, I wish you the best of luck for the homework.
Why are you not here?
And we will discuss, of course, the in more detail. So I think I will go back over this these concepts in the beginning of next lecture, and then the main idea is to introduce the SVM next time. Okay.